deeply rooted traumas. Don't be fooled. Don't be fooled by how ill-adjusted I seem. Okay, so today we're going to look at double displacement reactions. And again, this, as a concept, should be review from last year.
Yes, probably.
So if a single displacement is like a date gone horribly, horribly, horribly wrong, what's a double displacement like? I wasn't going to go brothel. Oh, you said thruple. I wasn't going to go thruple either, because it's not thruple. It's weirder than that, isn't it? It's like, because what it is it's like we've got a little date going on here, and we've got these two, and they're there hanging out. Look at them, and they're doing their thing. And then over here we've got these two, and they're on a date, and they're doing their thing. What color haven't I used yet? I haven't used a green. Yeah. Well, yeah, you don't want to make anyone feel left out. So yeah, we've got these people on a date, and in this case, I don't know, they probably need names. Give me a name.
Cat.
Cat?
Yeah.
C or a K?
K. Whatever
K it is.
S.
All right. Quiet, you. A name?
Susan.
Susan it is.
No, we've already had a Susan, guys.
She can get a new partner.
No,
Are you saying she can't get a new partner?
Susan.
Okay, that's fine. Hey, shut up. Okay, give me a name.
Dave.
I heard a Rachel and a Dave, so there we go. I got Rachel, I got Dave. Okay, so Kat and Susan, Rachel and Dave are on a double date, and Kat and Susan have been going together for a while. They seem to get along. Rachel and Dave, they've been a couple for a while. They seem to get along. Everyone's going good. And they sit down to dinner. Where are they going? I don't know. Maybe to... No. You don't double date at Arby's. Double date. Also, Susan's already been burned at Arby's. All right, she doesn't need to learn her lesson twice. She realizes that the temptresses behind the counter at Arby's can serve. Yeah, I think Swiss Chalet.
No, Swiss Chalet.
It's nice because it's connected to the Arby's. No, it's connected to Arby's. That's okay.
Step down. I feel like it's a step down. Taco Bell.
We're going for a nice sit-down meal. My friends, we're going to Swiss Chalet. They got that little dipping sauce, and at the end, they bring out the little water with the lemon in it. Do they still do that? I haven't been to a Swiss Chalet in forever. But I always like that little bowl of lemon water. That's nice. That's a touch of class. I should do that at home. Just at the end of a meal, just put a little thing out with some warm water and lemon. That's nice. All right, so it's Swiss Chalet, and they're chilling out. And, all the while, Kat there with Susan, couple, but just can't help but notice Dave's, just alluring eyes. And, oh, my God, he's so interesting. And he knows so much about Norwegian death metal, and I never realized that was a topic that was of interest to me. And yet now it's all I want to talk about, right? And Kat just smitten. And, Susan should be offended by this, but she's far too busy noticing that Rachel's hair just catches the light in this certain way that really is majestic. And by the end of the evening, what has taken place, my friends? They have swapped. And who is leaving with whom? Kat is leaving with Dave and couldn't be happier about it. And again, you would imagine that Dave's partner and Kat's partner would be so upset. But this is what's the beautiful case here, is that nobody's upset. Because who else is leaving with whom else? Yeah, we have swapped partners. And there we go. And this actually, because the only thing that actually drives anything in the universe is low energy state. In other words, stability. This is just a more stable arrangement. Lo and behold, what they thought was going to be a double date to Arby's has led them to a more stable arrangement.
No, Swiss Chalet.
Oh, sorry, Swiss Chalet.
Wow.
I forgot. I got confused.
This is lore. This is lore.
Yeah.
I'm invested.
Yeah.
Right?
You wrote Susan again?
Yeah. And again, who's to be upset about this? I would argue nobody. Nobody's losing here. Everybody's winning. So, in a double displacement reaction, you can think of it a bunch of different ways. I think the easiest way is just to say they swap cations, right? In a double displacement reaction, the easiest way to think of it is that two compounds swap cations. And so they would take the general form. Of some compound A with B. And keep in mind, of course, we have no idea what numbers might go with that, and it doesn't matter. You just balance them. Is going to react with some other compound, C and D. And again, we have no idea what numbers go with that, and it doesn't matter because you just balance it when it's all said and done. Are going to react to form what instead? What will the product arrangement look like with the letters we've chosen here? Yeah. Yeah, very good. A will end up with D, and C will end up with B. And even though that ends up being out of alphabetical order, by convention, we're still going to make sure A is in the front and C is in the front because those would be the cations, right? And again, all those question marks just mean I don't want you to think from the general form that it's always some one-to-one relationship, right? How do we have to figure out the formula of each product? Well, just like everything else, we have to work it out, right? We gotta put the time in. And, of course, this will be much easier if we just do an example. So, let's do an example. So, exempla gratia 1. Calcium chloride is going to react with sodium carbonate. Calcium chloride reacts with sodium carbonate. All right. So if we're reacting calcium chloride with sodium carbonate, yes, sir?
So up there you said in double displacement reaction, two ionic compounds swap cations, but in the thing you showed, like the four people, like this one and
Well, they swapped. You can think of it either way, right? The important thing is they swap, right? Like, yeah, if you want to think of it as swapping anions, that works just as well. Absolutely. So, yep, that's totally fair. All right, so you'll note that all those Unit 1 skills are coming in super handy here because we have to figure out the formula of calcium chloride. Calcium wants to lose how many electrons? We look up there, 1, 2. It's going to lose 2, which means that a single calcium would lose 2 electrons, 2 of them would lose 4, 3 of them would lose 6, right? And et cetera, et cetera. What about chlorine? How many does it want to gain? Just 1. So one of them could only gain 1, 2 of them could gain 2, 3 of them could gain 3. Where does that obviously meet up? At 2 lost and 2 gained. So how many calciums do we need? Do we need 2? No, they give 4 away. We need 1. Very good. And how many chlorines do we need? 2, because 2 of them can gain 2. So the formula for calcium chloride is CaCl2. It's a big dumb rock, so what's its state matter going to be probably? Solid. But if we're going to make this reaction happen, what are we probably going to do with it? We could melt it. That would take a lot of heat. So what's easier? Gas? That would take melting it and then boiling it. And rocks don't boil easy. Probably we're going to dissolve it in water. Does that make sense? Usually these reactions are done in aqueous solutions. So we're going to take that and we're going to dissolve it. In fact, all the double displacement and single displacement reactions we work with in this class, we're going to work with in aqueous solution. Yeah?
So can this test for assignment if we forget on like one of the lines to put like an aqueous or liquid, like how much do you drop off?
What I do is I catch you when you're on your way out of the school. I just run you right over, right with my car. Yeah. I think that makes an example of you, and then nobody else will forget, right? So you don't want to be the first, is what I'm saying. You want to make sure you're the second person to forget that something is aqueous. If you're the first, I'm recording this right now, so I want to be clear. That's a joke, and I'm obviously not being serious.
Well, what happens if you're the second?
Totally kidding. So, like, obviously, what I really mean is I'd take off half a mark.
Half a mark being half of your body.
Okay. So anyway, only kidding. So that's calcium chloride, and what's it reacting with? With sodium carbonate. And again, what do we have to do to figure that formula out? Yeah, we can't just assume it's going to be sodium and carbonate, right? We have to actually check to see the formula. Sodium wants to give away how many electrons? 1, which means that one of them will give away 1 electron. 2 of them will give away 2 electrons. 3 of them will give away 3 electrons, etc., etc. And carbonate is CO3, -2. If you don't know that, where can you look? Yeah, we gave you the table of those, right? So you don't have to have that memorized. You will eventually, I promise. You're going to do this to death. But if you don't have it memorized right now, that makes no difference. Which means that one of them can take 2 electrons, 2 of them can take 4, 3 of them can take 6. Where does that match up? Yeah, 2 electrons given, 2 electrons taken. For that to happen, how many sodiums do we need? 2. How many carbonates do we need? 1. And so the formula is Na2CO3. And again, if we're going to do a double displacement reaction, we're going to work with this aqueous. Yeah, it's a weird word, right? Aqueous, but it means dissolved in water. If you put these two solids together, nothing's going to happen. There's nothing energetically favorable for the most part with ionic compounds interacting with each other as solids, because as solids, what are ionic compounds? Big dumb rocks. But if we dissolve them in water, we can get them to react. So this is going to be in aqueous solution. And we said they're swapping partners. So right now, who's calcium on a date with? Chlorine. Who's sodium on a date with? Carbonate. After the swap, who's calcium going to be on a date with? Carbonate. And we can look at that. What charge does calcium take? What charge does carbonate take? -2. Do we need to draw a little chart? No, they match. What's the formula? Very good. CaCO3. And that should still be aqueous, in theory. Though we're actually going to, well, we'll talk about that later. The thing we discover with that is, and we'll talk about this later, is that actually doesn't dissolve in water. But that's okay. We'll worry about that later. What's the other compound? Na, which wants to lose. And chlorine, which wants to gain 1, right? Second to last. So its formula will be NaCl, right? Remember, you don't count over from the left. You have to say, right, like you don't include that last column, right? Chlorine's 1 electron away from a full shell. And we'll talk about its states of matter in a minute, about what we get as a product here. But that's the basic rundown. Calcium chloride plus sodium carbonate gives calcium carbonate plus sodium chloride. Is this balanced? What am I going to need to balance it? This one actually balances pretty easily. How many calciums here? How many calciums there? Okay, so far so good. How many chlorines here? How many chlorines here? What do I need? Great. Did that change my calcium at all? No, so we're good. How many sodiums here? How many sodiums here? Good. How many carbonates here? 1. Yeah, not 3, right? The 3 is part of carbonate. You got to watch out for that, right? It's CO3. That's the whole thing. So there's only 1 of them. If I had 3 of them, what would I have to put around CO3? Brackets, right? And then another 3. And how many CO3s do we have here? 1. If you wanted to count that as 1 carbon, 3 oxygens, you can. But I wouldn't get in that habit. I'd get in the habit of treating an ion as its own thing. Because if you have an NO3 here and then CO2 there, you don't want to have to count those oxygens together. Just count them as whole ions. It'll make your life much easier. All right. And that's balanced. We happy with that? Yeah. If you want to know the steps, some people like to have steps. My steps would be like this. 1, solve it with words. Right? In my case, before I ever did what we did above, I'd do what we did together as a group, which I'd just say, okay, we know that calcium chloride swaps with sodium carbonate to give what? Yeah, we'll put them in the same order as above. Calcium with carbonate and sodium chloride. If you wrote that a little bit too big, what you could do is you could just highlight it with your... I mean, why don't I just go on to the next page, or the next line, to give calcium carbonate and sodium chloride. And then my step 2 would just be to find the equation, or find the formula for each compound, the formula for each species. Right? And this is where your highlighter can be helpful, right? Like calcium chloride, figure that out. And we did the math up here. We saw that CaCl2. Oh. And then sodium carbonate. We said that sodium carbonate was Na2CO3. And obviously you saw how we had to do the math up above. Calcium carbonate is CaCO3. And finally, sodium chloride, which we probably all know by this point. If you didn't know it before, it looks like that. And then step 3 would be put this into an equation and balance. I had a couple people mention to me that they find it helpful to have sort of steps written out. So hopefully if a couple people mentioned it, usually there's like 5 or 6 people thinking it. So hopefully that is of some use to you. I don't know why I put steps 1 when I could have put step 1 and not looked silly. So I'm going to replace that. So steps 1 is 2. And then we will go to steps 2's. I always associate that with, I have family who are from out east, and they'll always talk about having a beers or a couple of beer, and I'm like, we're just doing this backwards? This is the thing? We just, when referring to beer, we just switch plural and not plural. That's the thing. And apparently that's what they do. I don't know. Yeah, we'll have 2 beer. Be like, okay. At this point, beer is like sausage, where the singular and the plural is the same. I always said sausages, and then I've been informed by numerous people that it is the singular and the plural are both sausage, like moose or sheep or what else? Yeah, fish. Mind you, read the King James Bible and it talks about loaves and fishes. So I mean, these things are but I think typically we say fish, 1 fish, 2 fish, red fish, blue fish. How's that feel? Okay, not too bad? All right. Now you're going to do an example for me. And the example you're going to do for me is exempla gratia due, mercury 1 chloride, and ammonium hydroxide. So take a few minutes. Work that out. You'll probably need that periodic table of the radicals because ammonium, that's a radical. It's our only positive radical. And then mercury 1, well, it's right in the name. Hydroxide's a radical. So, yeah, maybe you remember them.
I please excuse the interruption.
Yeah.
Could we please have the bond Stanford in guidance?
I didn't hear the name. Oh, yeah, of course. Oh, you're welcome. Yes. Solange Stanford, yeah. I heard Stefan too.
So did I.
Okay, now I feel less bad. Because I was like, I don't believe I have a Stefan. And then there's that horrible moment you're like, have I been teaching Stefan all semester? And at no point realized I have a Stefan. Anyway, that would be embarrassing. All right, get this, make it happen. Oh, yeah. What's the symbol for mercury, team? Hg, like Wells. It is blue. Why is it blue? No, you know this. Why is it blue? Because it's liquid at room temperature. What's the only other thing on the periodic table that's liquid at room temperature? Bromide.
Alright, let's go, guys.
Yeah. Look, gallium becomes liquid at a very low temperature, but it is solid at room temperature. So just like warming it with your hands will melt gallium, but it is solid at room temperature. Gallium's fun stuff. Not especially. Mercury's toxic.
Okay.
Mercury is just
Yeah. Now today I have to finish hanging some Right, how we doing? Do you need a couple more minutes?
yes.
All right, take your time. The one thing I'd say before you do anything else, let's just make sure we're on the same place here. We've already got the reactants, so to put it in words, what will the products be? Just the names of them. Yeah, and specifically mercury. Yeah, mercury 1 hydroxide. And who can give me the other one? Someone else. Somebody else. What'll the other product be? Mercury 1 hydroxide, because they're going to end up on a date together, and an ammonium chloride. Very good. So see if that helps you. That's kind of that first step, right? Is before you even do any like real figuring out formulae or anything like that, just figure out what you're looking at. What's going to be the products? What are they? What are the products going to be? Really be. No, that's okay.
Okay.
You're not splitting. So the ammonium is going to stay ammonium, and the hydroxide is going to stay hydroxide. Right, hydroxide is a radical, ammonium is a radical. But they're two separate radicals. Yeah, that's right. So you're going to have a weird thing where you're going to have NH for OH. So you're going to have H appearing twice. And the reason we don't like count them together and call it like NH5O is because this H is stuck to hydroxide and those 4 H's are stuck to nitrogen. Yeah, no, that's a good point. That's the first time we've come across two radicals where the same element appears in both of them, right? And we just treat them as totally separate things. And that's why we put those brackets around them, and that's why I said when you balance this, don't count, in this case, we're not going to count H's. We're going to count ammoniums, and we're going to count hydroxides. Did that answer your question?
Yeah.
It's a miracle. And the broken clocks right twice a day. That's just digital. That's just wrong all the time. Yeah. No. If you need them, but does it just that? If you need 2 of them or 3 of them, do you need 2 or 3, or is it just work like that? You just write like that. Don't leave the big gap. Same with that one too. Keep them tight. It's a single compound. I'll give you 3 more minutes. Use them well.
I don't know.
Sorry, I'm tired. I wasn't helping the table. At least we read funny filters. See, so I don't know what you're asking. That's great. Yeah. It looks like that one person the Addams family.
Is it a long story?
Thank you. He has like the worst back compliment I got. My brain.
Although
that she's had.
I guess doing those
When I'm not even dating them. So why does my weight matter to you? I love my brother.
So when he does something like slightly more boring, he finds you should try and influence him to like focus electronics. But you might like find that boring.
If ammonium has no charge, how am I supposed to plus? So then, the formula doesn't change.
All right, talk to me. Where are we at? Shall we do this? We're going to need to figure out formulae. So let's start with mercury chloride. What is the formula for mercury chloride? And we're going to have to do this over and over and over and over and over. Mercury, in this case, wants to give away how many electrons? 1. How do we know that? Because it's in the weird middle spot in the periodic table. We could look it up, but actually I don't have to look it up in this case because it's in the name. It's right there. It's telling me. Mercury's weird because mercury 2 is actually just a diatomic mercury 1. It's really weird. Mercury is the only cation that can be diatomic. So you could really call it Hofbrinkel. Hofbrinkel. Figure it out, team. Because mercury can also be diatomic, but we're not using the diatomic mercury. We're just using Hg plus 1. And chlorine wants to gain how many? How many electrons does chlorine gain? Uno. Therefore, ergo, the formula is HgCl. Good. Okay, and again, if we're doing these reactions, they only work if they are dissolved in water, right? What are we reacting this with? Ammonium hydroxide. Ammonium hydroxide. And so ammonium hydroxide would be NH4, which wants to have a charge of what? And hydroxide is OH, which wants to have a charge of... Do we need a table for that? No, what's the formula? NH4OH. Now, weird to have hydrogen in two places, but don't combine this into NH5O. It's important to keep those two radicals separate because this is ionic, right? Good. Now we said on the other side, this is going to form what? What's this going to form on the other side? Well, we said the first product will be mercury 1 hydroxide. Mercury 1 releases 1 electron, and we said hydroxide must have received 1. Do we need any subscript or any numbers? No, it's just HgOH. I picked this one to be nice and easy. And what's the other product? Ammonium, which is NH4. That gives away 1 electron. And chlorine takes -1. So the formula for this is NH4Cl. How's it for balancing? Yeah. And you don't count, again, hydrogens, count ions. How many mercuries? How many mercuries? Awesome. How many chlorines? How many chlorines? Awesome. How many NH4s? The whole thing? No. 1. How many NH4s? 1. Good. Very good. And how many OHs? And how many OHs? So this is balanced. Good. Okay. Now, of course, you are all screaming a really obvious question at me. You're all thinking, but wait. Well, let's look at example 3. Because the obvious thing is this reaction happens, right? And they swap partners. Cool. Okay. What about taking, let's take mercury 1 hydroxide, and let's react that with, what could we react with? I got an idea. What if we reacted that with ammonium chloride? What are my products going to be? Mercury chloride and... Oh, okay, so that reaction will happen. Okay, great. But then what if I put mercury chloride together with ammonium hydroxide? Then what would happen? Do you see what I'm saying? Well, think about it. If this reaction happens, if I put these two things together and they make these, well, if I put these two things together, why don't they just swap partners again?
Since they're like higher on the thing.
Well, the problem is though, the problem with that thinking is they're both, it's not like the other one where only one thing's getting kicked out. They're both getting kicked out and they're both kicking each other out. So I don't think you can use the activity series, right? Because wouldn't the activity series just tell us who initiates the kicking out? It would tell us that the higher one initiates the kicking out, right? But that's not going to answer when they're both kicking each other out. And the way we know they're more stable, exactly right. This will only happen if one of the products is really stable. And as it turns out, the way to know a product is really stable is if it's really stable, it's so comfortable being a big dumb rock that it won't even dissolve in water. Does that make sense? You're going to get a stable product because as it happens, way up here, the mercury chloride is dissolved in water. The ammonium hydroxide is dissolved in water. But this product here, mercury hydroxide, it won't dissolve in water. It's what we call insoluble. And that's really important. That note here, this is insoluble, which means it doesn't dissolve. So that means that compound is very stable, right? It's a very low energy state. Because if it's so stable that, well, other ionic compounds dissolve nicely in water, it won't, that's going to stick around. Does that make sense? Eventually, most of the ionic compounds we find out in nature are non-soluble ones. Because what happens on Earth all the time? Rain. And so as things are reacting and chemicals are forming and breaking away, all of the chemicals that dissolve nicely in water tend to either react away or end up in the ocean. Big one being sodium chloride, right? We know that the ocean's full of salt water. But the things that are left behind tend to be these very stable, low energy state molecules. Yeah. Great question. And I'm going to get there in like 14 seconds. But it's the exact right questions. I love that you asked it. So as it happens here, when we go to do this reaction, this would be a solid, this would be aqueous, but if we tried to get the products, mercury chloride would be aqueous, and ammonium hydroxide would be aqueous. But as a result, there's no stable compound, and because there's no stable compound, we get no reaction. So a double displacement reaction will only happen, we're going to say that here. A double displacement reaction only happens the less common spelling of happen with only one P, I guess that would be happen, will only happen if one of the products is stable to the point of insolubility. I.e., it won't dissolve in water. No, that's when the reaction will happen. See here, one of the products is solid, and so this reaction happens. On the other hand, here, both of the products are just aqueous, so it doesn't happen. Because this solid that you're starting off with is actually more stable. Does that make sense? And if the thing you're starting off with is more stable, it's not going to react. It's just going to chill out and do its thing. Does that make sense? So you're not going to get a reaction to happen if you don't have a stable, solid product. And by the way, it doesn't have to be a solid. What kinds of things don't dissolve? So at least one product will be either a solid or it could be a gas or it could be a liquid. Right? It's possible to produce a liquid that won't dissolve. What happens when you have two liquids that won't dissolve in each other? You've seen this before. Yeah, you've ever mixed oil and water before, or oil and vinegar or whatever? They sit atop each other, right? And obviously, if it produced a gas that wouldn't dissolve, what would you see? If you mix two liquids together and they start to produce a gas, you would see, I mean, not necessarily smoke, but you definitely see, yeah, I'm thinking bubbles. Bubbles, good, yeah, good. And if it forms a solid, does anyone know what we call it when you mix two liquids in a solid forms? We call this a precipitate. That's a solid forming from liquids. Reacting. My friend Chris bought me a shirt that says, if you're not part of the solution, you're part of the precipitate. I very much like it, but I've gotten too hefty to wear it. But I'll either buy a bigger one or get skinny one of these days. Likely buy a bigger one, because I like that shirt. If it was a liquid, what you'd see is 2 layers of liquids. And if it was a gas forming, you'd expect to see bubbles. Now keep in mind, other things can cause this to happen, right? You could see bubbles because it's boiling, right? You can see a solid forming because it's freezing. But in this case, it's the result of the reaction. Does that make sense? So, no matter what, this is going to be the form of one that works. You're going to have some aqueous compound plus some other aqueous compound, and they're going to yield a compound that is a solid, a liquid, or a gas. The other compound may also be solid, liquid, or gas, but it could also dissolve. That's fine. Only one of the products needs to be stably insoluble, but at least one of them has to be. This will be the sign that the reaction actually takes place. This is necessary if the reaction is going to occur. Necessary for reaction to occur. Because, if you can imagine, if everything just stayed aqueous, how would you possibly know that a reaction has happened? Do you know what I mean? If you have aqueous this, aqueous that, and then we say they react, and everything's still just aqueous and dissolved at the end, there's no evidence that a reaction has taken place. So now, what does that physically look like? It physically looks like this. We have some beaker that contains an aqueous solution, and we add it into some other beaker that contains an aqueous solution, right? And we put this one into that one, and what we end up with is a beaker that initially has twice as much liquid in it, right? And then it's either going to produce a solid, which means we will get a solid forming that we call the precipitate, or we'll get that beaker forming bubbles because it's producing a gas. Or you'll get the situation where you have 2 visible separate layers of liquids. And I'm going to show this by using 2 kind of different colors of blue and show like that. So layered liquids. By far the most common of these will be a precipitate because as a rule, we're going to be working with ionic compounds. And what are ionic compounds? Big dumb rocks. So if they don't dissolve, they tend to form big dumb rocks. Now, if you want to know what will and won't dissolve, we need a table to look up solubility. I'm going to give you a table that gives you a guideline. If you want the full and complete answer, in the bad old days, we'd break this guy out, and we would look up the specific solubility of every compound. And there's thousands of them in here. The good news is today, you can go to Wikipedia has an absolutely wonderful solubility chart, solubility table of ionic compounds, Wikipedia, and if you want to, you can look up just about any compound you can think of. So if you wanted to know, in that last example, we said that the reason it works is what forms a solid? Mercury hydroxide. So we could look up mercury hydroxide. I'm going to have to say 1 here. And we'll just scroll through. And That just so happens to not be in here. But if you look at all of these numbers for mercury, the secret with mercury is that they are overwhelmingly pretty hard to dissolve. This one actually doesn't have mercury hydroxide, but if you look, the lower the number, the things that are highly soluble are like up in the hundreds, right? And then the insoluble things are like this. How much iron hydroxide can you dissolve? 5.255 times 10 to the negative 5 grams in 100 mils. In other words, functionally none. Does that make sense? A tiny little bit will dissolve, but functionally not very much at all. Even iron oxalate, 0.008 grams per 100 mils. Functionally nothing. Whereas, if you get iron perchlorate, you can dissolve 300 grams in 100 mils of water. That's actually 3 times as much mass as the mass of the water. Not tomorrow. The Monday we're back. I'll give you a little chart where we learn to read that. Have a wonderful day. Be kind to each other. No homework today. Labs